All right, I guess we can get started here. So it's great to have Dr. Misty Bentz here. She's visiting us from Georgia State. So she got her PhD from Ohio State, where she overlapped with some people here. So Jen, Aunt Louie, and Darren. And then after grad school, she took a postdoc at UC Irvine, which is where we overlapped. And so she was there for 2 years before she got a Hubble Fellowship, which she kept at UC Irvine. And then she moved to Georgia State in 2010. So she's been there since then. She's now an associate professor there. And so yeah, she studies supermassive black holes and EGN. She's done important work in reverberation mapping and understanding the EGN broadline region. So that's what we're going to hear about today. So welcome.
Thank you, Jen. And thanks for having me. It's lovely to be here in the conversation. I admit I've been to various parts of Texas, but I hadn't been to this specific area of Texas before, so thank you for having me. For those of you who don't know, just to put in context where Georgia State is, we very often get confused with Georgia Tech, which is actually about 3 miles away, also in downtown Atlanta, but we are right in the heart of Atlanta, which is a terrible place to be if you're an observational astronomer, because you have a lot of light and really terrible weather. But we make it work anyway. So I'm going to start you out with something that hopefully everybody knows. One of the big legacies of the Hubble Space Telescope, which I'm waiting anxiously to hear about the gyros on it and how it's doing, is that we've learned that basically every massive galaxy has a supermassive black hole in the center. And this is not something that was known or even really anticipated before Hubble flew. And so it doesn't really matter what kind of galaxy you have, if you have an elliptical galaxy, if you have a spiral galaxy, if it's star forming, if it's not star forming. It really doesn't seem to matter. They all have supermassive black holes in the centers. And the story starts to get a little more fuzzy as we get down to these little irregular galaxies, little train wrecks. It's not clear what's going on with them. Are they the incubators for baby supermassive black holes? Do they even all have supermassive black holes or not? That is one of the open questions. But when we're talking about massive galaxies, they all have supermassive black holes. And so that actually brings up a lot of questions. In particular, which came first, the galaxy or the black hole? It's a little bit of a chicken or an egg type problem. Do we have little proto-galaxies in the early universe? The first generation of stars, maybe they're very massive, they live short lives, they explode, they leave behind stellar mass black holes that then coalesce and form the seed for the supermassive black hole. One idea. Perhaps we had very overdense regions in the early universe that just collapsed directly down into a black hole that then accreted material and grew with time. Primordial black holes, perhaps. It's another possibility. And so this chicken or egg problem is very intimately tied to where exactly did these supermassive black holes come from? How did they start in the early universe? And then how did they grow over time? What is the main growth mechanism for a supermassive black hole? Is it through mergers of individual black holes, sort of like the ones that LIGO has started finding? Or is it mostly through accretion of gas onto the black hole? And then when we look out in the universe, what we see is that these black holes can have a huge effect on our host galaxies. So if you look at one of these radio galaxies, for example, you see these huge jets of radioplasma being emitted from the center of the galaxy, and they're in fact shooting completely outside of the galaxy, running into everything along the way. Gas that might be trying to form stars is being heated up and shut down. And even the intergalactic medium itself is circumgalactic medium itself is being affected by these radio jets. So we know that black holes can play a big part in a galaxy's life cycle, but we don't really understand the details of how that works exactly. And so there are a lot of big questions that are still kind of open in the field of supermassive black holes. And one of the keys to trying to answer any of these questions is to be able to measure the mass of a black hole, because the mass of a black hole is what sets how much energy it has, how much gravitational force it has, basically sets how much of an effect it can have on all of these scales. So how do you measure the mass of a black hole? Black holes are invisible, so that makes them a little bit hard to study. But we can see their effects on things around them that are visible, so stars or gas. And the best example is the center of our own Milky Way galaxy, where you watch 2 decades of near-infrared monitoring of the positions of stars in the center of the galaxy. Allows you to trace out several stellar orbits, including this particular guy, which they've seen an entire orbit and a half over that time period. And by using the characteristics of these particular stars and their orbits, what you find is that the mass of black hole in the center of our galaxy galaxy is 4 million times the mass of the sun. All right, very simple, almost Newtonian diagnosis. So that's great for our galaxy. There's this lovely video I can show you. Anybody who's ever done, even general level physics can understand. Okay, you've got an orbit, so you can figure out the mass of the thing in the center. But what about all the rest of these galaxies out here? Right? We want to try to understand why galaxies look different from each other, and some of them look the same, and how they look different in different environments. All these sorts of questions you might want to answer. You're not going to be able to zoom in on this galaxy and find individual stars moving around in the center, because it's just too far away. So everything is all blurred together. So what are you going to do instead? The Milky Way is the only galaxy so far that we can use that particular technique. Well, there are a couple different options. If you're really lucky and you find cold molecular gas in the center of the galaxy and it happens to be arranged in a warped disk at just the right viewing angle, you might find water masers, which will allow you to very nicely trace out the Keplerian rotation curve of this disk of molecular gas and then very accurately constrain the massive black hole in the center. But you notice that I said if you're lucky enough to find this and lucky enough to have that and lucky enough, right? So water masers are an option, but they're relatively small in number. Okay, stellar and gas dynamics are another example that you can use. So here you're using the unresolved bulk motions of stars or gas in the center of a galaxy. So you measure the kinematics at various positions as close into the center as you can, and then you fit various models to those observations to constrain the gravitational field as best you can and determine how much of that gravity is being added by the supermassive black hole, and thereby constrain its mass that way. But you'll notice here that we've got this particular scale, right? Your radius, you're trying to get as close to the center as you can, right? Sub 0.1 arc seconds in order to really see the effect of the supermassive black hole in this object. And so here you're really limited by spatial resolution, which is distance. So these techniques are best used only up to about 100 megaparsecs. All right, so you're not going to be able to study anything outside of sort of the local neighborhood of galaxies with these techniques because your spatial resolution is going to kill you. So what are we going to do about black holes, maybe at cosmic distances? If we want to be able to provide some observations to pin down what our cosmological simulations are telling us, we should have a redshift 0.5 or redshift 1 or redshift 2. The only way you're going to be able to study black holes at those distances is to use active black holes, right? So we can see active black holes all the way across the universe out to redshift 7. At this point, I think 7.1 or something is the highest redshift quasar that's been found. But we can see them all across the universe. They're nice little spotlights telling us, hey, there's a supermassive black hole here. And so if we want to probe how galaxy formation and evolution and black hole formation and evolution are changing as a function of time and compare them to the universe in a box, kind of simulations that people do, we're going to have to use AGN. They're the only black holes we can really see at large distances. Okay, and this works because AGNs are really, really bright, right? So just to make it clear exactly how bright they are, this is a WIFPIC-2 image of an AGN. And there is actually a host galaxy there. You can't see it until you block out the central point source. And this smudge right here, just to remember, that's a galaxy that has hundreds of billions of stars in it, and you can't even see the galaxy because the quasar is so bright in the center of this galaxy. All right, so this is why we're able to see them all the way across the universe. In fact, people actually argued for a while whether quasars had host galaxies associated with them because they couldn't see them because of the glare of the black hole. Okay, so for our AGN, if we want to try to get a mass measurement for an active black hole, we again need some sort of a test particle that we can see to sort of figure out what the gravitational field is around the black hole and constrain its mass, right? And so I'm going to remind you with my cartoon here that I'm legally obligated to show as an AGN astronomer. Every AGN astronomer shows this figure. What the different pieces are of photoionized gas and dust and stuff around the black hole when it's active. All right, so in the very center, you've got your black hole with the accretion disk around it. That's what makes it active, is the accretion disk. And there's a region of photoionized gas at somewhat larger distances from the accretion disk, maybe not arranged in a spherical manner. This is just a cartoon, but larger scale than the accretion disk. And we see broad emission lines from this region. So if you're looking with a kind of face-on view, you can see into the center. You'll see continuum emission from the accretion disk. You'll see broad emission lines. That's a Doppler broadened gas that's photoionized by the accretion disk. So that's why it's so broad. All right. And then you've got this obscuring torus, so out past the dust sublimation radius, dust is allowed to exist. And so there's a flattened amount of dust in sort of a torus or donut shape outside of the central region. And so what that means is if you're looking at this object from a different angle, you won't be able to see into the center because the dust will block your view. You won't see this Doppler broadened emission from the broad line region. You'll see just a single narrow emission line from each view at that particular spot. And if you happen to be looking straight down a jet, if there is a jet, that's when you get a blazar. We're not talking about those today. So we want a test particle that's telling us something about the gravitational field of the black hole. We need hot gas that's close enough to the black hole. And this broad emission line is exactly what we're going to use. That's our test particles, this broad line region gas here. It's obviously moving very quickly, which is why you get such a broad emission line. And it's therefore going to be our test particles for our black hole mass measurements. Okay, so put this into context, what is the approximate spatial scale for the broadline region in sort of a garden variety nearby AGN? So something a little closer to home, help you picture this. This is the orbit of Sedna. This is one of those maybe inner Oort cloud or outer Kuiper belt objects that was found in our own solar system. It has an aphelion, or furthest point from the sun, of about 928 astronomical units. It's about 5.4 light days. Okay? When we're talking about sort of nearby active galaxies, the typical radius of the broadline region is also about 5 light days. So we're talking about solar system size scales in the center of a galaxy that's something like 40 megaparsecs or more away, right? And this is for the most nearby ones. So we're talking about very tiny spatial scales at very large distances. So these are obviously structures where you're not going to be able to resolve with even the best imaging that our telescopes can provide today. Maybe not even with the next generation of telescopes. All right, so how do we do that? If we can't actually spatially resolve it, well, we use the variability of the AGN instead, and we resolve it in the time domain instead of the spatial domain. So AGN are variable. If you remember from any sort of class you've taken where you learn about AGN, this is one of their typical characteristics. It's a great way to find them. If you look for variable things in the sky, a lot of those things are going to be AGN. And just to show you how variable they are, this is one particular object, NGC 5548. And it had been studied for 13 years. And what you see here is a light curve, a function of brightness versus time, for the continuum emission in that particular AGN for about 13 years. And then on bottom here, you see that broad H beta emission line, this guy here, the flux of that particular emission line over that same time period. And what you see is that the variations are correlated between those two regions. And not only are they correlated, but in fact, the broad H beta emission echoes the continuum variability. Okay. So I have this very, very simple little model to sort of show how this whole thing works. Very simple. Here's your black hole. Here's your broadline region. Just a very thin ring. Let's pretend we make it simple, right, for cartoon purposes. Your telescope is over here. This is you. It's obviously not to scale. And what we see in these objects is that when there is an event where a lot of continuum emission travels outward, it photoionizes the gas in the broadline region, and the signal travels to our telescope. But what you notice is that these purple arrows here don't all arrive at your telescope at the same time. Some of them have a longer path length they have to travel to get to you. And so what that means is if you average together the response of the whole broadline region, the average time of arrival for all of those purple arrows is going to be tau here, r over c. Right? So this one takes 2r over c, this one's 0, both of these are r over c. You take the average time of arrival is r over c. We know what c is, it's the speed of light, yay! So that means we know what r is. Right? So we can actually measure the average radius of the broadline region by looking at the average time delay of a broad emission line in the center of an HM. So if we look at that with actual data, where it's not 13 years and you can't actually see all the details of what's going on, but a shorter program focusing on a similar kind of object, here again is the continuum emission over about 45 days. And you can see there's a very nice event, it goes up, it comes down, and it just kind of peters off. And echoed in the broad H beta emission line is the same signal, but it's shifted in time and it's blurred. Okay? So you've actually convolved this particular function here with the arrangement of broadline region clouds, and so you've got a delay and a blurring factor. And you can, by eye, just read off what the delay here is, and therefore know what the size of the broadline region is in this object at that moment in time. It's about 6 light days. If you do a cross correlation function, so it's a window function, you just line up the two until you figure out where they best match each other, you again find the time delay of 6 days. And I always like to show this example because it's really clear to the eye exactly what's going on. They're not all quite this nice to us. All right, so if you know the size of the region of gas that you're probing, and you know how fast that gas is moving, then by the same principles I showed you before with the center of the Milky Way, you can figure out what the mass of the black hole is in the center of whatever galaxy you want, right? Modulo a scaling factor that takes into account the exact arrangement of gas clouds, their inclination to your line of sight, things like that. So you get your time delay by taking observations of your object, and so I should point out these are spectra. Every single one of these points here is a spectrum that was taken on a different night. And so you take spectrum night after night after night after night after night after night for these objects so that you have information on both the continuum and the broad emission line. But once you've done that and you've built up your light curves, you can determine what the time delay is between the two of them, and that gives you the size of the broadline region. The speed at which the gas is moving in the broadline region just comes from the Doppler broadened width of the emission line for which you've measured the time delay. So those are not particularly difficult measurements to make. There's a lot of data processing that gets you to this point, but the measurements are pretty simple. So you get a line of sight velocity, you get a radius, you combine those, and you get something that's modulo a black hole mass. Okay? So, a couple things to point out. You might say, well, what if the gas is being blown away from the black hole? Maybe it's not actually under the gravitational influence of the black hole itself. Well, we expect gas that is responding to the gravitational influence of the black hole to show a relationship where V goes as R to the -1/2. Whether it's falling in or it's orbiting around, it's going to have that same characteristic. And for every object that we've been able to do this particular test, where we have multiple emission lines so we can measure different radii and different velocities, we find that this assumption holds true. Okay? So as far as we can tell at this point, it looks like there is virial behavior in the broadline region, which is good. And so we can then assume, well, if we can trust these measurements, then we need to figure out some way to deal with that F factor in our black hole mass measurement. Right? So I told you it was modulo the inclination of the system, for example, and the exact arrangement of the gas clouds. Since we can't actually take pictures and resolve what those clouds are doing, exactly how they're arranged, one thing that we can do, just to make things relatively quick and simple on ourselves, is to assume that the relationship between black hole mass and stellar velocity dispersion of the bulge of a galaxy, the M-sigma relationship, which probably everyone has heard of, that relationship is the same for basically any galaxy that's out there. Any galaxy should fall on that relationship. Okay. If we make that assumption and just figure out what multiplicative factor we need to apply to our black hole masses to make that true for our reverberation match masses, we find that the F factor required is about 4 or 5. Depends on exactly which objects you include, exactly how the measurements are made, but everybody tends to fall in the same region of 4 to 5 with the answers that they get. So this is great. This actually means it makes sense for a couple of reasons. If you figure out what inclination of the system this would imply, you find that the inclination that would be implied by this F factor is about 20 to 25 degrees. So that's great. It's not completely face on. It's not completely edge on. We know it shouldn't be edge on because we wouldn't be able to see it. The dust would be in the way. So that actually makes sense. And so this is generally what we do to calibrate our black hole masses and put them on an actual mass scale. Now there are a lot of potential complications with this shortcut, and so there's been a lot of work that has gone into examining this over the last couple of years. In particular, measuring stellar velocity dispersions of the bulges of galaxies for high luminosity AGN is hard, right? I showed you how bright AGN can be compared to their host galaxies. So if you've got a really bright AGN and you're trying to measure something about the host galaxy, you've got a contrast problem. One of the issues we've had, especially with the AGN, is that a lot of the bulge stellar velocity dispersion measurements have been made from long slit spectra, which can be a problem if you've got, for example, a bar in your galaxy. How exactly is the slit aligned to the bar? That can be a huge problem as well. Not everybody in the literature defines stellar velocity dispersion mathematically the same way. There are about 5 different mathematical definitions of that thing floating around in literature, and people just adopt whatever it is that they want, and then they mash a bunch of literature measurements together, and voila, right? So that's a little bit of a problem as well. And then there is some evidence to show that, in fact, the M-sigma relationship may not be the same for all kinds of galaxies. Barred galaxies may not actually lay on the same relationship that all other galaxies do, or galaxies that may have what's called a pseudo-bulge. So a bulge that's primarily grown through galaxy accretion rather than through mergers of galaxies. But they may not also lay on the same relationship. So this may not actually hold true at all, right? So it seems to work out okay so far, but there are a lot of potential problems here. So I will be coming back to this. So one way we can get around this F-factor business, it's really a fudge factor, right, is to just make full use of all of the information that's contained in our time delay measurements. So I showed you earlier that you get a time delay, but you also get a blurring factor, right? And so that blurring factor is really a mathematical convolution of your input signal and the response of all of the broadline region clouds that are responding to that signal. And so you can write it out mathematically, and you can actually try to carry out an inverse problem and recover what exactly is the blurring factor. And the blurring factor will tell you, as a function of velocity across the emission line and time delay, what is the response of the broadline region. And so for a couple of simple models, if you just have a rotating disk that's your broadline region, you would end up with, here's velocity, here's time delay. You would end up with a blurring factor, a convolution factor that looks something like this. It's symmetric in velocity, and it has both large and small time delays at the line center. If you have gas that's just falling into the black hole, you will get an asymmetric response. And if you have outflow, you'll get an asymmetric response the other way. So if you can actually do this inverse problem and constrain what the convolution is, you can figure out a lot about the kinematics of the gas. And you can also figure out a lot about how the gas is arranged geometrically as well. All right. And so this was actually something I was able to do as a postdoc for one of the best attempts we've ever had at this up to that point. For one particular object, we were able to pull out what the convolution factor was. It was sort of the perfect data set. The object was highly variable, so we had a nice strong signal. The variability was very coherent. It wasn't lots of little stochastic things, so we could really see the response very cleanly. And so this was the convolution factor we pulled out for that hydrogen emission line in optical. And just by glancing at the examples I've shown you here on the bottom, you can right away say it's not outflow. And it looks like maybe a little bit of rotation plus inflow. All right, so you can do the inverse problem. The inverse problem is hard. It's a noisy data set. There are gaps. It's not infinitely long. All of the traditional problems you have with inverse problems come into play here. So you can also do the forward modeling problem, which is just say, let's assume a model for the broadline region. Let's say what that would mean in terms of the response function, and then let's see how well that fits with our data, our observations, right? And so another person that I've worked very closely with, Brandon Brewer, and then Anna Pankos spent a lot of time working with this. They've actually developed a Bayesian modeling code to try and do the forward modeling problem for reverberation mapping data. for that same object, when I just showed you, they end up finding that the broadline region is a thick disk. It's inclined at something like 25 degrees to our line of sight. Yeah, they got it defined backwards here. And the gas seems to be doing a combination of rotation plus inflow, which is exactly what you just saw in the previous slide. And they can get out black hole mass without an F factor, because they've got the full dynamics of the system in their models, and so they can figure out what the black hole mass is. For this particular object, we found a black hole mass of log black hole mass of 6.82, or 6.51. This is the answer that we got with just a simple time delay, the velocity width, and an F factor. And you can see those numbers actually agree pretty well. We're not that far off when we adopt an F factor. And there's been 9 other AGNs, so a sample of 10 that we've now been able to apply this forward modeling to, and we find similar results for all of them. They're not that far off in their black hole masses from what you would get with the simple F factor approach I showed you before. Their broadline regions are thick disks, inclined at moderate angles to us, and there seems to be a lot of rotation and a varying amounts of inflow in the broadline regions of these objects. Okay, so they're still model dependent, obviously, and the models are a little limited in scope at the moment, but we're starting to learn some very interesting things about this region that, remember, we cannot take pictures of. This is really the only way to learn what's going on physically.
Oh, can I ask a question? So
Yes.
with the simple one, for the 9 comparisons, are the error bars always much, much smaller than the forward modeling? Because forward modeling, you're taking account of the different orientations.
Yeah, so the error bars for these guys are always just the measurement errors. So there's no, there's no systematics, it's just the.
Does the forward modeling always get a lower result, or do they flip?
Oh, they wiggle around. Okay. Interestingly, if you take all of these forward modeling black hole masses and infer what the F factor should be, you find basically the same answer we had before, which is 4 to 5. Okay, so I've shown you a few examples that rely on months of spectroscopy, right, in order to get these time delays to be able to pull out these interesting details. Clearly, we are not going to be able to do that for all the AGN in the sky across multiple redshifts when we want to actually figure out what's going on with galaxy evolution and black hole evolution, right? So what are we going to do about all these other AGNs out there? Well, luckily, one of the things we've learned from looking at these time delays in black holes is that there's a pretty strong relationship between the luminosity of the AGN and the size of the broadline region, which is not crazy because it's photoionized gas. You would expect that when you have a more luminous accretion disk, that the region of photoionized gas where a specific emission line comes from is going to be farther out. And when you have a fainter accretion disk, a less luminous accretion disk, the region of photoionized gas where that specific emission line is emitted is going to be closer in, right? And in fact, we find that is exactly true. And if you just do some very simple assumptions with the math, the relationship that we've now found empirically agrees very well with those simplistic photoionization assumptions. Okay, so this is the radius-luminosity relationship. I've spent a lot of time working on it. At the moment, it seems to hold over about 4 orders of magnitude. There's a fairly low scatter. These 2 guys, we think there's something wrong with the measurements. You can get aliasing in the light curves that would cause you to infer the wrong time delay. This is a known problem. There could also be problems with the luminosities. I can't remember. I looked at the details of those 2. There was something funny about the 2 of them. But for most objects, it does seem to hold pretty well. And so you can actually use that as a tool to avoid the whole multi-month monitoring program of your favorite AGN. Because you don't now have to measure a time delay. Now you can simply take one spectrum of your favorite quasar. You can measure the width of the line just as you would before. And then you can measure the continuum luminosity. And using this handy-dandy relationship, you can just read off what the size of the broadline region should be for that luminosity of an AGN. Right? One spectrum, 2 really simple measurements, really simple math, and now you have a black hole mass. And you can do this for millions of objects if you want to. You can take the entire Sloan Digital Sky Survey Quasar catalog with one spectrum per quasar, and now you have a black hole mass for every single one of them. Okay, it's important to point out that anytime anybody's estimating a black hole mass based on the spectral characteristics of any quasar, everything is bootstrapped and tied down to this relationship for H beta, which is for nearby AGN with an optical emission line. So using a magnesium 2 emission line in the near ultraviolet or a carbon 4 emission line in the ultraviolet, those are bootstrapped to this particular result. Okay. So obviously that gets you a lot of useful numbers that you can do all kinds of interesting cosmology with. But also you probably just realized when I was saying everything is pinned to this, that there are places where those assumptions can go wrong. Right? Okay, so I've solved everything for you. You can measure all the black hole masses you want. It's super easy. You can teach an undergrad to do it who knows nothing about astronomy. What else is there to do, right? We're done, right? I wouldn't be a good observer if I didn't say that more observations are clearly needed. And so I'm going to spend the last few minutes here talking about some work that my group is doing right now. One of the things we've decided to tackle is trying to look at the consistency in black hole masses across different techniques. So in a few objects, it's been possible to measure the black hole mass using more than one method. You could use this reverberation mapping, the echo method, or you can zoom in and see what the bulk motions of stars or gas are doing in the center of the galaxy. And then compare, how do those black hole masses actually agree or not agree with each other, right? If it's the same black hole, you should be getting the same number no matter what. And so basically, as of a few years ago, this was pretty much all that existed in the literature for directly comparing masses of black holes through multiple techniques. Obviously, we need a lot more comparisons here. And that's hard. There's a reason why there's only a few objects on that particular plot. And this goes back to things I was talking about at the beginning of the talk. So if you want to model the bulk motions of resolved stellar kinematics or gas kinematics, the objects need to be fairly nearby so that you have spatial resolution. And so that restricts you to the nearby universe. But if you want to study AGN, then those are pretty rare objects and they tend to be far away. So there's this very small region of overlap where you have an AGN where you can use this echo technique to measure the black hole mass versus it being nearby enough that you can actually zoom into the center of the galaxy and try to resolve what the stars or the gas is doing. All right, so disclaimer, this is never going to be possible for huge samples because we are working against limitations that we can't really overcome at the moment with the telescopes that exist. But it's possible for at least a handful of objects, so we should really actually be able to look at this. So we started the Southern Telescope AGN Reverberation Experiment. Everybody needs an acronym. I had fun one afternoon drawing our little logo right here. You can see the echoes coming off the accretion disk. Yes, it's very fun. And so the goal is to compare black hole masses from reverberation mapping and from stellar dynamics in a small sample of galaxies where we can actually do so. And so here is our progress at the moment in chart form. So on the x-axis we have the reverberation black hole mass, and on the y-axis we have a dynamical black hole mass, color-coded, red for stellar, blue for gas dynamics. There's only a few that are actually color-coded here. NGC 40, 151, and 3227 has measurements in all three. And NGC 4395 has a gas dynamical measurement and a reverberation measurement. It's a tiny little dwarf galaxy that doesn't even have a bulge, and so what would bulge stellar dynamics be? It's kind of hard to say. And then we have a few others that we've got reverberation masses for, and I have a few observations in hand that we're working on currently in order to do the stellar dynamical modeling to determine what the black hole mass should be for those as well. Plus a few more objects that aren't on the plot that are in earlier stages of progress. But we're hoping to be able to fill in a plot like this with at least 7 or 8 objects to really say, when you look at a black hole in the center of a galaxy and you use any technique, do you get the same black hole mass? Are we then talking about quasars at redshift 7 versus quiescent galaxies in the local universe? Are we talking about apples and apples? Are they on the same mass scale, or is there some sort of systematic bias between one or the other Are there assumptions that break down that we need to know about? Okay, so that's one thing we're working on. Part of this is in our recently approved JWST Early Release Science Program. So one of 13 programs, yay, me, is to zoom in on the centers of one of these galaxies and get stellar dynamical measurements so that we can do the modeling. And we're going to hopefully compare, do I have this on the next slide? I do. We're going to hopefully compare how well you can do from space versus the ground. So there's a few advantages and a few disadvantages to trying to use James Webb for something like this. From the ground, using NIFs on Gemini, for example, you don't have to worry about making your instrument small to pack it into a rocket to launch it into space, which means that you can have gratings with finer spectral resolution, for example. JWST, you have to make everything very compact, and so the gratings are going to provide a coarser spectral resolution. So we're not sure that we're going to get the spectral resolution we need to very clearly detect what the kinematics are. Yeah?
What will you resolution want?
So this is about 5,000,
Okay.
and this one varies across the bandpass. And it goes from about 2,000 to 4,000, but we're not sure when it gets up to 4,000 if we're going to find absorption lines there, because that's in an area that's not an atmospheric window we can probe from the ground. So it will be a surprise. We're hoping there will be, I think it's an OH absorption line that might be out there, and if we find that, we might actually be doing better. So spectral resolution, we're not sure how that's going to go, but we do know in space we're going to have much lower backgrounds, and so we're going to have a lot more signal and a lot less noise, which is going to be great. Also, in space we're going to be truly diffraction limited. There will be no atmospheric seeing that we have to worry about. From the ground, using laser AO, you always have an uncorrected seeing halo around your diffraction limited, corrected AO spike, right? And so that always is going to limit a bit how far into the center you can truly probe, especially when you have a big bright AGN in the middle and there's that big halo of uncorrected light around it that's just causing noise. So we're going to see how well we do whenever JWST launches, but that is coming eventually sometime in the near future. So in the meantime, while we wait for that, the particular object is this nice pretty galaxy that you see here, NGC 4151. We're currently working on reanalyzing the ground-based measurements that currently exist for it. They were some of the first measurements that were done with NIFs on Gemini several years ago, and so we've gone back through the whole pipeline and we're reanalyzing everything to try and see if we can improve the results from the ground so that we can then compare them with our new JWST observations. And we don't know, are we going to do better from space, or maybe not so well from space, or about the same, or I guess we will see. So stay tuned on that one. And in the meantime, we have lots of other things to keep us busy, so I spent a lot of my time looking at not just the black holes in these galaxies, but also the host galaxy properties themselves. There are a lot of scaling relationships that we use to estimate black hole masses or to try to compare with hydrodynamical simulations of galaxy evolution, for example, to see if our galaxies in a box actually match reality. And so I recently just published a paper with a lot of updated black hole scaling relationships using black hole masses from reverberation mapping and then measurements of various properties of the host galaxies. The bulge luminosity, the galaxy luminosity, the bulge mass, the total stellar mass of the galaxy. So we're looking at all of these different relationships to try and provide constraints for whoever needs to use them. And we've got even more work in progress. So I mentioned some of the problems with bulge stellar velocity dispersion measurements for our sample. And my former postdoc, Meredith Batiste, has actually spent a lot of time working on that. So trying to use IFU data to measure stellar velocity dispersions in the bulges that are much more accurate than the ones that had been previously used in the literature for a sample. And she's got a few papers on that. I've got 2 graduate students, one junior grad student who's learning from my senior grad student at the moment. They are working on the IFU observations that we have in hand to try and make the measurements of the kinematics of the stars in the centers of the galaxies so we can then model them and determine what the black hole masses in those galaxies are from stellar dynamical modeling. So they are quite busy looking at those. I've got another graduate student who's working on H1 spectroscopy of our host galaxies, so looking at the total gas mass of the galaxies, but also hoping to get some Tully-Fisher distances to these AGN, because in general we don't have very good distances for the objects. And you know that luminosity appears in a lot of these scaling relationships, and you have to assume a distance to get a luminosity. So we need better distances than we have, and so he's hopefully going to make a dent in those, which would be great. And one more graduate student who's working on a multi-wavelength study to pin down the bolometric luminosities and accretion rates for these objects using simultaneous observations that span a wide wavelength range. So we've got lots of things going on. We're working in lots of different wavelengths trying to tackle a variety of issues. And all of it feeds back to trying to understand how well we can measure black hole masses and then predict black hole masses in other galaxies. So hopefully I have convinced you that there's a lot of ongoing work, not just in my group, but in lots of other groups as well. But all of that work should put us in a place where we have better black hole measurements for nearby galaxies, which should then, in turn, feed into better estimates of black hole masses for all active galaxies across the entire universe. And once we have that, that's going to give us a better understanding of how galaxies and their black holes grow and evolve over cosmic history to create the universe the way that it looks today. So we're just going to answer everything for you, so stay tuned, and we hope to have that done soon. Thank you very much. I'll take any questions.
Anyone have any questions?
Sure.
Yeah, so way back about halfway through, you showed the scaling relation, the black hole sigma relation, and all of the things that you need to worry about, right? All of the biases.
Yes.
I guess one I'd be curious if you think should be on the list. Is there any reason to believe that the galaxies that are active might be unusual in some way? They might be more massive black holes, for example.
So there have been varying claims about that in the past. There was a claim that active galaxies actually did not fall on this relationship. What we find with the more careful measurement of not only the black hole masses but the stellar velocity dispersions as well is that they do seem to fall on the same relationship. So you'll find different answers in the literature, but from the work that my team has done, it looks like they hold up pretty well.
And then if I had a really technical thought, I think it's probably a dumb question, but you have now the correlation between radius and luminosity. I guess the square root is what the stronger and constant density case must give you, I'm guessing, or something, or is it not constant? I don't know.
Yeah.
It's close to the stronger theory we give you.
Yeah.
But that must mean the whole basis is the flux, the black hole accretion disk flux vary.
Yeah.
And now the stronger sphere must be changing too, right?
Yeah.
So how does that mess up reverberation?
It doesn't, only because we can't measure it accurately enough to see that particular issue.
Okay,
so,
it's not big enough.
No, but we do actually have AGM that has significantly changed their luminosity state over a span of a few years. So usually our programs focus on objects for a few months at a time. But if you go back and then look at that object again a few years down the road, it might be significantly more luminous or less luminous than it was, and so you'll measure a different radius in that object.
Yeah, that'd be great.
You will. And so there, for the object that's been studied for 13 years, what we find is that there's a radius-luminosity relationship for that object. As it changes its luminosity over time, the radius of the emission line
Does
changes
the velocity
as well.
change in such a way you get the same mass?
It does,
Oh, wow.
yeah. And so what's interesting is trying to see, do all the objects follow the population relationship? Where did I have it? Right, if you took an individual object and measured its radius and luminosity with time, does it have the same slope or does it have a different one? And that's something that we're still not quite sure about, simply because it's a huge investment of observation and data to be able to answer that. You have to monitor the same object multiple times over multiple years. So, hard to do on a postdoc lifetime or a grad student lifetime. Yeah.
Anything else?
Yeah.
Do you have a sense for how much scatter you would expect in the relation between the different measurement and mass measurements? Because it's in that range that you're looking at?
Yeah, so just for the ones that we're interested in looking at, or?
Yeah, I guess.
These one. So, I mean, this one, this sort of gives you a sense of the current scatter. Right, and it's not great. So some of these objects, you know, if you've got big enough error bars, the answers agree. In other cases, they really don't agree, and they're off by a lot, right? So part of what's difficult here is that when you talk about late-type galaxies, to do the dynamical modeling, you have to, at the moment, ignore things like asymmetries in the stellar kinematics that might be caused by a bar. There is no, currently at the moment, bar-optimized dynamical modeling code. So the group that I'm working with on the James Webb Space Telescope project, bring up their pieces again, all my animations. So Monica and Eugene are two of my good friends who do dynamical modeling. So they're the ones who actually write the modeling codes, and they are right now together developing a bar-optimized dynamical modeling code. And so that should help us, even in the study of this particular object. It's a weakly barred galaxy. And so if you really want to compare the measurements that you get from the various methods, you have to take into account things that might, assumptions that are not physically valid, such as assuming there's no bar when there is a bar. So we're going to hopefully be able to do that particular test, and that might help in some of those other galaxies as well, where the measurements are pretty disparate between the different methods. Yes, sure.
Can you just list the telescopes that you use regularly and like roughly how many nights per year you get?
Yeah, so let's see here. So as a grad student, I did a lot of observing at the MDM Observatory, which is near Kitt Peak. It's just down the ridge from the Kitt Peak National Observatory. We used a 1.3 meter telescope, and I spent lots of time there, but it's usually a team of observers rotate people in and out. Yeah, I think everybody at OSU helped observe for these things. And so those campaigns tend to last about 3 months, and that was every night. And so you'd look at several objects throughout the night, and then the next night you'd look at the same ones again. As a postdoc, I spent a lot of time using the Lick telescope, the 3 meter telescope. We had I think it was a 65-day observing run there. It was again all night long, and that was some of the other results I showed in the middle here. Currently, I use the Apache Point Observatory 3.5 meter telescope, and that's because they're great about being flexible with time. So they've allowed me to take the first hour of every night for 2 months, for example. So I don't have to have the whole telescope all night long and kick everybody else off. So it makes it a little easier to play nicely with others. And so that's all for the reverberation mapping. For the dynamical modeling, Gemini, I have my first approved BLT program for that, for a different target that's in the south, and then our JWST program as well. So I use anything and everything, anywhere that anybody will let me have class. Okay, anything else? Let's send this together. Oh, probably, yeah. I have not updated that. It's like 10 to 7.
You want a free lunch?